Yeah, so we are recording. So to those of you at home, welcome again. This is the second session in our journey into the fascinating world of quantum hardware. Without further ado, I will hand over to our friend Carlos. So Carlos, the floor is yours.
Okay, thank you. Thank you, Bambode. Thank you, everyone who is here. And well, today I was planning is like to show some guys some like calling short overview, a little bit of history of quantum mechanics, and because I'm already like to I want you guys like to have the idea is that like why we are using like a Schrödinger equation, why we need study the Hilbert spaces and all these things. So today I'm thinking it's a very short review about things, experiments, and ideas that was like things that what happened in the beginning of the 20th century. And I will stop like in Schrödinger when we start Schrödinger equations. We will discuss a little bit some things, but I mean, it's not the, it's not my. Don't think that is a general historic review. I mean, there's more things that's not included here, but I try maybe, I don't know if it's, I'll get this goal in the end, but I'll try to give you guys the ideas behind the things related to quantum mechanics, like why we need to quantize, energize, and wave particle duality from light and from particle like electrons. And so the idea is to try to show a little bit from where these things came. So this, and after that we will have, not today, I mean, but in the following the course, we will have like the study, like the math behind these ideas. I mean. So the thing is this: the ideas today we try to see to understand a little bit the ideas behind quantum mechanics, what motivates people to do these things, and then this will be a complement. The lecture today will be complemented for when we see the math things, that we'll discuss the postulates of quantum mechanics and Hilbert space and all these stuff. Okay, so I don't know, maybe if I was like talking with Bumblebee, if the things I'm showing here is too short and you guys want something more to get more details about the things that I will talk today, so we can have another section maybe next Friday, where I'll show with more details the things, because I'll show something about 25 years in about 1 hour. So these things here, I'll talk about this. Usually this is a 1 semester course, like in the usual in the undergrad physicist course. I mean, about quantum mechanics, the first quantum mechanics course. So this is about 1 semester. So I'll say things here in 1 hour, and maybe it's to, if you want to understand better, if you guys want to understand better, maybe we can like have another section to describe with more details all these things we'll discuss here. Okay, so I will show so how these ideas I will finish, as I told you before. I'll finish here with the Schrödinger equation, but all these things happens before to get the Schrödinger, the hints to find this equation. Okay, so let's try to understand a little bit today. And again, if it's too short, we can return maybe in other section, and I can show with more details the things that I'm talking today. So we start about these things here about which called today black body radiation. But the thing is, the study of radiation emitted by a heated body in equilibrium is considered since the 19th century, like Kirchhoff, Wien. And the idea is, if you have like a body with a cavity, a small cavity, and you put radiation inside this cavity, light, and the radiation here will be bouncing back and forth inside this box. It's like a box, and the thing is this box will get heated because this radiation inside, and once it's heated, it can like emit radiation also. Okay, so experimental result shows that the radiation emitted from this cavity, that we call like the black body, was related to the energy density of the radiation inside the cavity, as well with the temperature. So, I mean, the radiation emitted was something like this, I mean, for different temperatures and as a function of the frequency need, the frequency for the emitted light that is getting into the box, the black body in the box. So the spectral radiancy of the black body radiator as a function of the frequency for different temperatures. So we see that a dependence from the temperature and the frequency. Okay. So this is like an experimental result. So the theory tried to explain this was no, the people using like, because we are this, I think this is wrong. I think this is 1990. I think I forget here. No, it's okay. It's right. It's the beginning of the end of 19th century. Yes, okay. So it's right. The data is right. So it's about in 1900, Highland proposed this. He calculated theoretically using like, because by this time the theories knows from people was like Newtonian mechanics, the Maxwell electrodynamics, thermodynamics, and optics, right? Geometrical optics. So using like things from especially thermodynamics, Highland, he find an expression like that to explain this behavior here. To explain things like this. Where rho here is the density of the radiation. Kb here is the Boltzmann constant, and T is the temperature. N is the frequency, C is the light velocity. So he found his result in this. People could see that this is true only for small frequencies, because for big frequencies, if you calculate like the total energy per unit of volume, you need to integrate this in the frequencies. And once you integrate this for big frequencies, you get a result at infinity. Okay, so for big frequencies, this will increase. And was the experimental results were shown. So for big frequencies, the thing is going to zero, not to infinity. If for small frequencies, this could be zero, and it's okay, it's agree. Small frequencies, it's agree, but for big frequencies, it doesn't. So this is known in the literature today as the ultraviolet catastrophe, because the classical things from this time could explain these results here. How a black body emits radiation. So it was Planck how evaluate how to using some properties from thermodynamics that could find an equation like that. I mean, he basically used like to find something like that. He used like the fact that the exponential here is very important, as you can see, because for big frequencies, this term goes to 0 like this. And he could do this only when he assumed that he could find this result only when he assumed that the things or the energy inside the cavity should be quantized. I mean, because he could, let's show something here. He could like use the fact that exponential of something. This is this thing, right, over n. In other words, it's a sum. A sum where n should be 0, 1, 2, 3, and so on. So during his calculations, he could found this exponential using this, like this trick. Okay, I'll not get into the details. So that's why I'm saying, if you guys think that I'm too superficial today, so in the next Friday I can get more details about at least some of the things, because today I want just to get the ideas behind. So that's why he found an expression like that, and this expression could fit well the experimental results. Okay, here is again the radiation, the density of radiation per wavelength here. So wavelength is just the inverse of the frequency, but it's okay. So this is these small dots here are the experimental results, and the solid line here are this formula, Planck formula. Okay. So Planck obtained this formula considering the dynamical equilibrium between the emission and the absorption of the radiation by the cavity. They only making the assumption that the radiation of the frequency E could only be emitted or absorbed in quantity of energy, where any edge E. I mean, a trick that he used to get this exponential was using the summation instead of integrals. That it's what is done in general. But the sum, the sum says that you don't, you cannot have like only quantized values for n, only integral values of n, right? So, and it's proportional to this constant whether he could fit the data. The constant is something like that, which is called today Planck constant. So this constant is here inside. So Hν, the energy, and Kb is this is the energy to the temperature. It's the Boltzmann relation. Kbt. Kb is the Boltzmann constant and T the temperature. And here is the energy that Planck found. So the conclusion is that the energy inside the cavity to explain the experimental results must be quantized. That's the thing that Planck concluded. To have this result, to explain the results for big frequencies, so the energy must be quantized, because it's the only way that he could get this result here. Okay? So, okay. So this is one point. Second point, another thing that was known by that time is what we call today photoelectric effect. But this is known since from the 19th century. Hertz was the first to see that the ejection of electrons from the surface when incident light get into the surface. And the classical laws by that time said that the electrons should be emitted with energy proportional to the light intensity. Thus, the magnitude of the current would be proportional to the light intensity, right? The number of electrons would be proportional. But what was observed is that the energy of the electrons emitted should not depend on light intensity. This is the observation. The observation that Hertz obtained. The observation that Hertz obtained. It observed that it depends linearly with the frequencies of the incident light. So not for the intensity of light, but with the frequency of light. Okay? And the classical physics by that time didn't explain this result as well. So it was Einstein who proposes in 1905. He, in some sense, he generalized Planck's idea. I mean, Planck is from the end of the year 190, right? Planck ideas was from 1090, 900. So Einstein in 1905 generalized, 5 years after Planck, generalized his ideas and said that light interacting with matter reveal quantum behavior at low energy. In other words, he says that light exists in quanta everywhere, not only inside a box when radiation is getting into. That was the Planck said, I mean, 5 years before. So Einstein came and says, no, this is not only a particular thing that happens inside a cavity that emits radiation, that is get light inside it and emit radiation. That is a general property of the light. And this light with certain frequency incides on the metal to explain the photoelectric effect. This light would incide the metal with a certain number of quanta, each one with the quantity h ni. That was Planck postulate to explain the black body radiation. It's the same thing. And then the quanta would collide with the electrons, provide the energy necessary to escape from the metal. So it's basically all these things are basically shown here in this picture. Again, this was an experiment did by Millikan. I don't have the data here, but I mean, was by that time. So what could see is from a frequency smaller than a certain value, and here he used like a sodium atoms, and a value is smaller than this one, 5.6. Nothing happened. No electron was emitted. But for a frequency bigger than this, 5.6, you have here this small balls here, white balls here. This is the electrons, the emission of the electrons. And so Einstein proposed that these electrons emitted as a kinetic energy from this type. M is the mass of the electrons. And this is the difference of energy. So this is H ni, the quanta of energy that get here. And this is the energy necessary to have the electrons ejection. The energy needed to separate the electrons from the metal. So if this party is bigger than W, so the electrons will be emitted. Okay, so what Einstein did, he just used the Planck's idea now to say, look, this is not inside a box anymore. This is just a metal, and light comes into the metal, I mean the sodium here. Okay. So this is the second point. Okay, I'm not sure if I'm doing too fast. I don't know if people has questions. Maybe I should look. I don't see button. Okay, no questions, right? Okay. Hi, George. I didn't see you before. Okay, so George is looking if you have questions. So let's keep going. So we had, so far we had like the idea from Planck that energy should be quantizing to explain the black body radiation. And now we have the Einstein generalized his ideas to tell us not only inside the cavity that energy should be quantized. It should be quantized. This is in general, not only in not only inside a cavity. So the other thing is what you call Compton effect. So Einstein proposed that the quanta of energy should also manifest outside the black body cavity. Yeah, and he could explain the photoelectric effect. In fact, this explanation was the explanation that gave the Einstein the Nobel Prize some years later, 20s. However, this did not lead him to the notion of quantum radiation as a particle. I mean, today we know that the photoelectric effect would be enough to have the conclusion that the radiation, that light, could behave like a particle. But by that time, Einstein didn't notice. No one noticed this property. I mean, it's about in 1905, right? It was only in about 1916 that he was analyzing the concept of gas, of quanta. He was led to the prediction that quanta of light, that called today photons, carries momentum and energy. And that was when he proposed this in about 1816, and that was an experiment done by Compton, who showed this effect. I mean, basically, he showed that the photon or the light could behave like a ball. Like in these classical examples when we are studying like momentum, conservation of momentum and energy in classical mechanics, classical mechanics classes, we see in this case like a photon or a light is coming and it hits an electron and gives this electron, the photon will have like energy and momentum, and as well the electron. I mean, this would work like a billiard ball, right? So this was Compton interpretation, is that a photon of wavelength lambda incident on a free electron at rest will give a collision, and the photon would be scattered with an angle theta, with some wavelength length L naught, I mean, which is bigger than lambda. So this was like the definite, let's say, experiment that gives the idea that light could behave like a particle, not only because we know before from the electromagnetic theory that light, from the electrodynamics, Maxwell electrodynamics, that light behaves like a wave. And here now we have the result that show light behaving like a particle. So okay, so far we have light with we can think like a quantum of energy to explain the black body radiation, to explain like the photoelectric effect. And now we also see that light could behave as a particle. So we have the duality, wave-particle duality for light. Okay, so this is the Einstein suggests this in 1916, but the experiment was about 23, 24. Okay, so we have these properties for light, but from the same period, people was also worried about the structure of the atom, atomic structure. So in the end of the 19th century, people like Thomson, J.J. Thomson, Röntgen, the Becquerel, and the Pierre Marie Curie, he provided the tools for better understand the structure of the atom, like the study of radiation. Röntgen found the X-rays. The Thomson with experiment show the particle behavior of the electrons. So with this, people was like worried to understand what's the structure, real structure of the atomic structure. So returning now a little bit in the past, in 1897, Thomson, J.J. Thomson, measured the ratio of charge of the mass of the charge and the mass of the electron that show that the electron should behave, should be think as a particle, right? Which was the preview from the classical theory, the Maxwell electromagnetism. But the experimental proof was only did in 1897. So with these ideas, Thomson proposed, and he was also worried about the structure of the atomic structure. He proposed this model for an atom. So he proposed that a sphere of positive charge, it's embedded with electrons with negative charge. Okay, and the total would be like a neutron. Now, would be this atom will be neutron with no. The balance for positive and negative charge would be the same.
We have a question from Diego.
Yeah, please.
It is a bit unclear to me what the property is, one that makes a photon a particle. Is it the fact that it has a quantized value of energy, or is it having the ability to exert momentum to a massive particle?
Yes, it is exactly this response.
And
he gives momentum for.
Yeah.
Yeah.
And why is having any of the properties sufficient to call it a particle and not just a wave with these capabilities?
Oh, this is like this, like once he's colliding with the particle, in this case the electron, he gives the electron a change. He gives the electron momentum, right? Momentum and energy. K here is the energy. The electron here is at rest, and the proton. The photon comes and gives the electron the momentum energy. So this is a behavior like a particle, not a wave, right? the behavior like wave, you would have like things like interference and things like this. That was also known from the classical electromagnetism, from Maxwell classical electrodynamics. So the wave properties was known before, but this things here is new. These things here would be, it's like they behave like a particle. Okay.
Yeah, if I could add to that, a classical wave, like on the ocean, can carry momentum. It can push you. But I think it's the discrete amount that a photon pushes that makes it a particle.
Yeah. I mean, they're both things. Okay. So, okay, if no, we can return. I mean, about these things. So okay, let's see again. In the Bohr, the ideas behind the Bohr atom. So at the same time, people was worried like to explain these properties for light. Other people was worried to explain the properties from the atom structure. So again, the Thomson proposed a model like that. I mean, a sphere with positive charge embedded with electrons. And okay, this shows some problems with experiments, because one of the predictions is that if you send, let's say, alpha particle here, I think he's calling alpha particle is like something like the nucleus of the helium atom, I think. I don't remember. In other words, it's a particle with positive charge. If you send him it was expected that this particle was bouncing inside the atom if it has this structure. But this was not this was the prediction from the theory. But the observation is that most of the time that you send these alpha particles inside the atom, it seems that nothing happened unless you pass for some region. Let's show you. So it seems that most of the time you send these alpha particles here, nothing would happen. Unless when you pass from some region here, close, much smaller than the size of the atom, that something would appears. Another question?
Looks more like a comment than a question from Konstantin. If the photon energy is greater than 8 rest masses of the electron, there will be more complex phenomena.
Let me see.
So it looks more like a statement than a question.
If the photon energy is greater than 8 rest masses of the electron, that would be more. Yeah, I'm not really sure. Yeah, I don't understand well what he means. More complex phenomena.
Maybe we can get back to that at the end.
Yeah. So the things that was observed was that the when you send like the alpha particles in the atom, in general, just in a region much smaller than the atom size, we would have something happen, some bouncing. And most of the time, nothing would happen. So it seems that this model here, the Thomson model was not the correct, right? Otherwise, could happen. This bouncing back could happen everywhere. But what was shown is something that it seems that something in the center has the most of the mass of the atom. So here is just an example of trajectory, but here is ZE, where is the charge of the nucleus, and just close to this place, a behavior similar like that would happen. Okay, so this model, it seems, is not good enough to explain the experimental, the observational results. So it was proposed by Rutherford that a positively charged nucleus attract the negatively charged electrons. And the first law has a behavior like this, 1/r², where r is the distance from the nucleus and the electron. And the electrons will travel in a circular or elliptic orbit about the nucleus, something similar with the planetary orbit. So the problem here is, even in the theoretical point of view, because the classical electrodynamics will tell us that accelerated charge, in this case an electron around the nucleus, would radiate, and this radiation will make the electron lose its energy. And you could also calculate, estimate the value by the time that the electron would collapse inside the nucleus. That would be something about 10 to the minus 10 seconds to a nucleus of 10 to the minus 10 meters. So about 1 angstrom. Okay? So the Rutherford model had some like theoretical problems that people, I mean, even by that time, people was like, oh, it seems that's not the correct model basically because of these things. So, okay. And then came, so another thing is the classical electrodynamics was also enabled to explain like this, it seems, quantized behavior about the spectra, the atomic spectra. Like in the case here I'm showing is for the hydrogen atom that people, these guys here, evaluate in the end of the 19th century. You can have an expression like this. This is the wave number, which is proportional to this R here, which is the Rydberg constant for the hydrogen atom, is something with the inverse of length. And this is the energy levels for the atomic, the hydrogen atoms. So the final and the initial level. So for the, let's say, for the Lyman series, this guy here is something like that. So the final is the level 1, the lowest energy, right? And the end can be like 2, 3, 4. And the Balmer is this, and Paschen is this, and so on. Balmer starts in the final is the level 2, and the initial will be 3, 4, 5. I mean, this formula was obtained by experiments. People make experiments with hydrogen atom because it's the simplest, and they find that spectral lines was given by a formula like that. And classical electrodynamics could not explain this as well. Okay? So this is the electron, when I say the levels, the energy levels that the electron should be. So when the electron make the transition from one to another, so an expression like this would happen. And, sorry?
Konstantin has commented, expanding on his question, as at photon energies greater than or equal to 8 mc squared, a pair of electron and positron will be born. Therefore is a limit on the energy of the described model. I don't think quantum computers matter.
I think quantum computers don't matter. Yeah, the thing here that I'm showing today is not everything related to quantum computers. I think the idea is the quantum mechanics as well. So what he's saying, a photon energy will be born. Okay, a pair of electron and positron will be born. There is a limit that the energy of the described model. Yeah, but I mean, it's a comment, but it's not the things. I mean, the idea today is just show the ideas behind quantum, some ideas behind quantum mechanics. So I'm not talking about quantum computer yet, because the thing is, we have these things today, and the next we'll have the math tools about quantum mechanics. So the thing is just to people understand that the necessity for these math tools is do something else that came before. I mean, some ideas that came before that lead us for the like Schrödinger, things like Schrödinger equation, and then the necessity for studying like Hilbert space and so on. So okay, but thanks. I mean, it's a nice comment. So let's. So okay, so other things that like classical physics know by that time was not explaining well. So we have the problem with the structure of the atom, and some also experimental results that the classical theory didn't explain about the change in the energy levels, the transition the electron to energy levels of the atom. And then came Bohr ideas. Okay, he basically postulated around 1913 that an electron in an atom moves in a circular orbit, like Rutherford said, about the nucleus under the influence of the Coulomb attraction between the electron and the nucleus, and obey the laws of classical mechanics. Okay. But the thing is, instead of the infinite number of orbits, because let's say in between the orbit 1 and orbit 2, in classical theory, we have infinite numbers of orbits, right? You can have an orbit in the classical theory like 1/2 or 2.5, something like that. But this is not the case. So this is not the case for Bohr. So instead of the infinite number of orbits, which would be possible in classical mechanics, it is only possible for an electron to move in an orbit for which its orbital angular momentum is a multiple of h. In other words, it's quantized. Okay? H bar appears here is the Planck's constant divided by 2 times pi. And n is like a number, like 0, 1, 2, 3, 4, so on. integer number. And the other thing is, despite the fact that it's constantly accelerated, an electron moving such a loud orbit does not radiate electromagnetic energy like the classical theory said. It just like postulates this, like the rule that he decides. And thus its total energy remains constant. So once you are in an orbit, despite what said the classical theory, now you for the Bohr rule, for Bohr, one of the Bohr's postulate, say that no, this will not happen because this is what was observing, right? So electromagnetic radiation is emitted only in one possibility. If an electron initially moving in one orbit, let's say EI, changes motion to move in another orbit, let's say EF, and the frequency of the emitted radiation is equal to this quantity. So H, again, the Planck constant, is the frequency and the difference of energy from one orbit and the other orbit, so initial and final orbit. So once it's one orbit, it does not radiate, but if it changes one orbit to the other, it radiates with a formula like this. I mean, Planck's ideas behind this again, right? So 13 years after. So that's the Bohr model. And with this model, who could explain these formulas? And here's, I think this picture is not that good, but this is the representation. This is the lines that I show here. Appears here in these figures. This is the Lyman series, Balmer series, Paschen series. These three here. This series here. There are more that he can also explain, but let me show only this here. Okay, so this is the experimental results for difference like wavelength and frequency. So Bohr model could explain this, which is a great success because Bohr atomic model was an enormous success and a big step forward. Remember, then after that, I mean, when we have the Schrödinger equation, Schrödinger also can show this with more detail. But I mean, we are in 1913, and more than 10 years before the Schrödinger's ideas, and that's why this is enormous success, because it explained for the hydrogen atom, for the other atoms, for instance, the Bohr model doesn't work anymore, just for the hydrogen. So this was an enormous success and a big step forward. However, it's important to note that this is the simplest quantum model of the atom, and more sophisticated tools were still necessary. Okay, but I mean, this was a really big step. So, okay, so we have questions now?
No questions.
So, we have so far some new ideas coming from trying to understand the properties from the light, and we get the conclusion that light sometimes can behaves like a particle. So we have the duality, light, the wave-particle duality for light, and also some people was worried about the atomic structure. That now the best model that we have is this Bohr atom structure that explain well behaviors in the observations in the hydrogen atom. Right? So more ideas is coming, and the other is related with de Broglie and matter waves. So in 1923, de Broglie suggests that the dual wave particle nature of the radiation should have its counterpart dual wave particle nature of matter. So in the same way, radiation has this dual behavior particle wave. So the same could happen. Should also there should be the same similar behavior should also appear for the matter as well. So particles for de Broglie ideas should have wave properties. The wavelength associated with the particle should be something like the Planck's constant divided by the momentum of the particle. So this idea was like proved in some experiments, and this is an example. A comparison of X-ray diffraction pattern and the electron diffraction pattern. So here, the thing is the incident beam of X-rays, which is radiation, right? Or electrons coming from a crystalline film, and we'll show like the structure here in this photographic plate. So here's the left is the results for the X-ray, the Debye pattern of X-ray diffraction for this type of crystal, zirconium oxide crystal. And in the right is the pattern from electrons in gold crystals. Okay, so it shows that electrons has also like a wave structure, right? Very similar here with the radiation. And another more known example is the bit split, the double slit experiment. And you send some, in the case, electrons passing here for a difference of potential, and they show this structure here, structure like that, and you can see like that wave properties here. This is, I think, this experiment was in the past they have that like animation showing the experiment, but yesterday I looked for and the video didn't work. I don't know if it was a problem for one day. But they have a lot of nice experiments here in this website. But this is the result, I mean, for electrons again. But the wave properties is not only for electrons, it's the other type of matter like protons, neutrons, and so on. So at least matter that is from atomic size. We don't know for bigger matters. I know people try to see some properties today from things like virus or something like this, but so far I think it is inconclusive. But it would be interesting to see, because we don't. Once the thing we don't know the limit of quantum mechanics. We know, I mean, okay, it's work for atomic size, but we are not sure that this could work for other size. But I mean, this is other thing. It's not part of the talk today. So okay, so we have the the duality wave particle properties for light, for radiation, and from particles, matter particles. So we have this duality, and we know so far the atomic structure do Bohr, the things that we know so far. This is like a quote. I mean, a comment, just a comment. Because in 1897, we mentioned very quickly, Thomson, J.J. Thomson, discovered that the electron which he characterized as a particle with a definite charge-to-mass ratio, was awarded for the Nobel Prize in 1906. And his son, G.P. Thomson, in 1927, discovered electron diffraction. It was awarded by the Nobel Prize with Davidson in 1937. And so this comment here, one may feel inclined to say that Thomson, the father, J.J., was awarded the Nobel Prize for having shown that the electron is a particle, and the son, G.P., for having shown that the electron is a wave. So this duality in the family. So okay, but this is just a comment. So this is the thing so far. Now, I don't know about my time. Let's see. Time, yeah. I think almost 1 hour. Heisenberg picture and uncertainty relations. So the starting point on these ideas is 1925. And basically Heisenberg said, I mean, this is very short things about there is a lot of philosophy behind Heisenberg's ideas, but let's try to have a short one slide to try to represent his ideas now. So the only sensible way to formulate the mechanics of the system is observing it. And by observation, we mean any interaction experienced by the system, such as a scattering of light or electron and so on. So in the absence of interaction or observation, the system would be totally isolated from the outside world. And only by some form of, again, interaction or observation, the system would have a definite state. So what Heisenberg uncertainty principle results is from the realization that any act of observation on a quantum system will disturb it. So I think this representation here show this is the photon wavelength, like the Broglie ideas here, right? And the greater is the photon momentum, the shorter is the wavelength, and vice versa. So what Heisenberg says is basically, if I have a big wavelength and I want to know some information about the electron in this atom, this big wavelength here, in this case, will just tell me that the electron will be somewhere here, in the atom diameter. But I have an uncertainty because I don't know, a big uncertainty because I don't know where the electron exactly is. But because this big wavelength, I have a small momentum for the electron because the wavelength didn't disturb the electron so much. In the other side, if I have a short wavelength like this picture here, so I can tell, oh, the electron is not here anywhere in this orbit, in this energy level of the atom. It is located approximately here because now I have a shorter wavelength. But because I have a shorter wavelength, I disturb the electron. So I have better precision in his location, but I disturb it. And if I disturb it, so I have a bigger momentum. Shorter wavelength, bigger momentum in this second. Okay, so this is behind the Heisenberg ideas. So this the same thing here. Use photons to highest possible moment, shortest wavelength, to determine accurately the electron position. However, the electron will be disturbed by the high momentum of the photon, and so its momentum will be very uncertain. The essence of the Heisenberg uncertainty principle is knowledge of one parameter implied uncertainties on the other conjugate parameter, and this is the relation. In fact, we can find this relation in one way more more formal way, okay? And we probably will see this when I'm talking about the math tools of quantum mechanics. So as I say, this is like a complementary things. So we have today is only the ideas, and then we have another day the math tools, and the things will complement each other. So okay, Heisenberg, and then we talk a little bit about this important experiment last Friday. I mean, because we are talking about a little bit about qubits, but today we're not talking about qubits because the idea of qubits from that time was not known. What this guy want to show, in fact, in 1922, that just to measure the magnetic dipole moment for atoms they use like silver atoms, and they want like to show that the angular momentum, that's one of the Bohr hypotheses, is quantized or not. So setting a beam, a silver atom beam on an oven, get passed through a non-uniform magnetic field, and it will be detected here in this detector. And neutral atoms, the only net force that acting on them is like that. I mean, where B here is the magnetic field, and mu is the magnetic dipole moment. So, but okay. So since the force acting on each atom of the beam is proportional to me, right? Proportional to the magnetic moment, each atom is deflected by the magnetic field by an amount of mu Lz. Thus, the beam is analyzed into components according to the various values of mu. The deflected atoms strike the metallic plate, upon which they condensate and leave a visible trace. And the classical theory, we expected that they have results in between, continuous results in between minus mu and plus mu. And the reason is that classically the atom can have any orientation relative to the z-axis. But the thing that was observed was this. This is the classical prediction. This is the observation. So the prediction is that mu must have discrete quantized values. And once mu is proportional to angular momentum, so the experimental result suggests that L is quantized. So the angular momentum is quantized. Okay? That's one of the Bohr's postulates, right? Okay, so this is what this guy, Stern Gerlach, found in 22. Okay, in the end for today, so we want to get and we find like the Schrödinger equation in 26. Okay, so far we conclude that the wave particle duality from radiation and matter, and we have some extra structure from Bohr atomic, and the things like energy, angular momentum must be quantized. So basically, it's these things that we have. So following previous ideas like de Broglie's idea, Schrödinger developed the idea of particle waves into wave mechanics. His starting point was that wave equation that describes the behavior of light waves in space and time. And he described a matter wave equation that represents the behavior of matter. Schrödinger described the particle wave and shows how the particle wave function evolves in space and time under specific certain circumstances, and he gets an equation like that, something like this. Okay, but the arguments that guide him to these are basically four. Again, we will see this in next classes, next lectures, and we'll show how to get all informations behind this equation. This is today. Again, today is just like we have some ideas. So the consistency with the de Broglie ideas is one of the arguments. So these things, the de Broglie ideas for matter is valid. The relations from the wavelength and momentum, and the relation frequency and energy. It must be consistent also with the classical equation, like the conservation equation. Total energy would have a kinetic part plus a potential. It must be linear, because this is important comment, because once it's linear, we can, like, if psi is solution from the equation, so if psi1 and psi2 are also solutions, so I can sum both with some constant C1 and C2, and they are also solution in this sum. This is important because this can give me these wave functions can produce the constructive and destructive interference that are the characteristics of the waves. So we already know that particles have this behavior, right? Particles have this behavior because of the Broglie's ideas, right? And the potential energy is general a function of x and t, and however, there is a special case where it's constant. That's the case of free particle. So with these ideas, basically guide him. I mean, I just to have a general. Let's see here. Just I don't have too much time, but the thing is, using these ideas here in this, you could, like, it's the energy is something like this. We could use, like, de Broglie's ideas, where E is H and P square is H square prime lambda, right? And from the wave mechanics, we know this is this, and the angular frequency is 2p. So if you use these things here, we have h bar omega h by square k square prime. Okay, so this, I mean, this is not a formal proof of evidently, but this just these things behind show like Schrödinger that he needs something, and because he needs like a wave. So if I have a wave, This is like a wave equation solution proportional to this. So I have something that I need a first derivative in time here, because I can have this guy appears here, and something else that have a second derivative in space here, this guy would appear here. So this is just that suggests him how to get the right result. I mean, of course, there is a formal way to do that. I mean, I'm not show today, but this we will show when we have the math rules. And once I have only one derivative here in time, because it appears here only one omega, one I would be present. So some imaginary part would be present here. So okay. So that's exactly what we have. Here, right? A double derivative in space and a derivative in time. This is the kinetic part, the potential part, and the total energy. Okay, and the I appears here in the time derivative. Okay, this is just to have the notion that these ideas guide him to his equation. Okay, so the wave function of quantum mechanics is complex because the imaginary part appears in the equation. This in contrast with the waves in classical mechanics. For instance, a wave in a string can be specified by a real function which gives the displacement of the string. Okay, and the fact that the wave functions are complex make it apparent that we should not attempt to give the wave function a physical existence in the same sense that water waves have in physical existence. So it seems that the wave function, the psi, by itself has not a existence in the sense that we could measure it, like we do, like in his example with water waves. So what has existence is the probabilities. So the basic connection between the properties of the wave function and the behavior of associated particle is expressed in terms of the probability density, we call here P. So which is given with psi conjugate psi. Again, we have formal definition of this when we see the math tools, when we discuss like Hilbert space, because so far the guy didn't know about Hilbert space. Not I think that people, physicists from 20s, didn't study this. So he just will get the Hilbert space after that. We'll just understand that this is part of the Hilbert space. So we need to understand Hilbert space to understand quantum mechanics, like to understand the behavior of the small particles, atomic particles, atomic size particles. So these quantities specify the probability per unit length of the x-axis of finding the particle near the coordinate x at time t. Okay, so we will discuss this with more details when we talk about the postulates and the math tools. But I mean, the ideas that necessary to have the conclusion that we need a thing, a quantity like the psi that is complex, that we need to understand things like the Hilbert space came before all these ideas that was happening in the early of the 20th century. So the interpretation, I think we're late now. The interpretation is that the probability, we cannot say that the electron is located in one position. What we can say is, once you solve the Schrödinger equation, and we can say, oh, the probability to find the electron, this is my solution. So probably the electron is in a place where the amplitudes of probabilities, of amplitudes of that waves, are bigger. I mean, these waves, the amplitudes of psi is bigger. So the electron should be, probably would be in a region like this, or this, or this. Low probability that he would be in this region because the amplitude is very low. So in this case, the electron is here, is located here. So it's the only thing that you can get from the equation. So the probability to find the in this case the schematic picture for the electron. So if you have an orbit like atomic ball, so we can tell the probability to find the electron in some places in that orbit. So with the Schrödinger equation, we are able to show that the electron wave function can assume only certain discrete energy levels, which is the Planck's ideas before Schrödinger, right? So in the Schrödinger equation, this is still valid. These energy levels are the same as the energy of the electronic orbits of the hydrogen atom postulated by Bohr. So the things that Bohr did in the past, postulating, like some rules that he defined, it's valid here. I mean, the Schrödinger equation say, oh, okay, Bohr is really right, at least for the hydrogen atoms, right? For the other atoms, Bohr system didn't work. And the particle wave function is an extremely significant concept which we shall use frequently during the course. We'll do this during the course. So yeah, but still need some definition, specifically some math tools to we understand better. And here's just an example. The simplest example, like we consider the hydrogen atom. You have the Schrödinger equation, something like this. The potential for the hydrogen atom is something like a Coulombian potential. And this is the electron charge, and this is the Schrödinger equation in 3 dimensions. I mean spherical coordinates, because it's the more appropriate coordinates to solve this problem. And this is the solution. We can solve this using, like the previous, the prerequisite courses, short courses about differential equations. If we use some of the techniques, we can find the solution from this equation. You can separate for variables and solve for the radial theta and phi coordinates. So the solution is something like that. I mean, this n and l, I didn't talk about this today, but it's not quantum numbers. So n is 1, 2, 3. I mean, L varies from 0 to n minus 1. So if n is 1, L is necessarily 0. And m is this is the principal, it's called n is the principal number, quantum number. Principal, L is the azimuthal, and m is the magnetic. It varies from minus L to L. So if L is 0, m is necessarily 0. If L is 1, m varies from minus 1, 0, and 1. So 1. And this is the solution from this equation for the problem for hydrogen atom. This is spherical harmonics, special type of function, and this I think is Laguerre function. And this whole here is just this, where A is these things here is the Bohr radius. So okay, I mean this is just an example. And yeah, so but the thing is, this is from 26, like Schrödinger's equation. I think this is Phillips, not Phipps. Phillips and Taylor in 27 used the Stern-Gerlach technique on beam, but now using hydrogen atoms, and he concluded that there is another important quantized quantity, which is called spin, and has the a quantum number associated with it, which in the case of electron, it can plus or minus 1/2 of these things, which is related with the Pauli exclusion principle. Okay, and we will use the ideas of spin a lot, but in case of quantum mechanics, in Schrödinger equation, the spin is not included. The only quantum numbers that present at these three, it's not related with the spin. So in the case of Schrödinger equation, the spin comes like an extra postulate. Okay. But if you Schrödinger equation, it does not include the spin. It also is not relativist. I didn't talk about relativity today, even spatial relativity, but it's another idea that was happened during this period. The spatial relativity given us by Einstein is from 1905, and the general relativity is from 1915. But it's not relativistic. Schrödinger equation is not relativistic in the sense of spatial relativity is not included. And a equation that includes both the spin, that don't need an extra postulate, and is also relativistic, is the Dirac equation. But I mean, we will not use Dirac equation in this course. That's why, I mean, I'll stop here today. And I mean, I hope I could show some, at least the ideas. It was worrying, like the ideas would be clear. If not, two things, we could like make another lecture about these things, and I could try to explain better some of the behavior, some more examples or something like that. Or I mean, this is a type of material that you guys can find like on the internet. If you prefer go ahead, we can like talk about all these things. What is next, at least in principle, but it can change. I mean, this is not the need to follow this exactly. I mean, I can talk a little bit more about the things that we talked today. But in principle, the other is the mathematical tools of quantum mechanics, because this would be like a complement from the things that we saw today. So I think, I don't know if people have questions. Okay. Okay, vamos there. I think.
Yeah, well, fantastic. I think given this historical context, this journey, gives people a great idea. I think it's the best way to learn this topic, because very often people, when you start with the postulate of quantum mechanics and, mix up with maths and these things, it gives the impression like the theory came around because, some math physicists, they decided okay, we are sick of classical physics. We just, we will invent something new. It's actually the opposite. They resisted initially. They wanted classical physics to explain this, but the experiment was not backing them up. So this whole thing led to the form, to how we know quantum mechanics today, and its applications, obviously. So it's very important, this historical contest. And Carlos, you've done. I'm sure all the audience will agree. It was a fantastic sequence of the physics behind. So someone is making a comment.
Yeah, I agree with Baron. I read the.
Oh yeah, he's recommending a book, Carlo Rovelli, great book. Yeah. So I think it's really important. This not at least later when you come across the mathematics, the abstract mathematics, you will remember some of these other stuff, like the stuff that he was talking about, like, for example, the uncertainty principle he mentioned. This is just one thing that comes to mind. You will see from a formal point of view, this has to do with the non-commutativity of the operators, the self-adjoint operators that you learn about on Hilbert spaces and so on. So yeah, so this is really great. I wouldn't actually mind, before we start the mathematics, if you wanted to add another session, like a final one in the historical contest, to go through some of the other stuff that you didn't mention, and you wanted to cover, and then we can then begin the mathematical thing.
Okay.
But this is something we can discuss offline next week in our thing.
Okay, one thing I was thinking, maybe because I didn't talk about quantum computing today, maybe how these ideas came for the computer scientists
as well. Yeah, so maybe you can add. This will be the next thing we can do, definitely. We can get up with the we can look at to add, and then we'll have the mathematics then come in. So Carlos will take a bit of break, and then you resume again. That's it. We take it from there. Yeah, but well done. I think it was a great session, and I think everyone will agree with me. Does anyone want to make any point? Because I know we are like over half an hour thing, but it was worth it. Anyone wants to make any final comments before we disconnect? I will even stop recording now. So for those on YouTube, I'll see you in the next lecture. I will stop recording now so people can feel easy to come and make any comments if they want.